Spectroscopy allows us to analyze those colors and determine an object's temperature, density, spin, motion, and chemical composition. Crash course.
Alrighty. Questions, comments, concerns? Alrighty then. Okay. So you should take out your packet from Friday of notes. If you weren't here, you need to go to the blue hanging folders and grab one, please. If you do not have a calculator, I suggest grabbing one today as well. We are going to quickly recap the last thing that we talked about on Friday, and then we're going to get into some new stuff. So if you were not here Friday, you'll need to get the notes from Google Classroom, fill those in. Majority of that was review, so. All right, let's get started. Let's review what we left off with on Friday, where we started talking about electrons and the color of light that can be emitted. So we talked about how an electron, when it's in its lowest energy or its normal or most stable state, is called its ground state. And this is where the electron wants to be. But we can add energy to the electron, similar to what we did on Thursday for the flame test lab. Okay, the flame being the energy, or possibly another good example is electricity, okay, to these electrons to where they become excited, and these electrons will absorb wavelengths of light, okay. This added energy causes our amplitude of the electron wave to increase, which, as you recall, hopefully from Friday, this gives them that ability to jump between energy levels, okay. This is very unstable for our electron, and this extra energy is released as the electron returns to its ground state, which is that original level. And I briefly told you, I think the last thing that I said Friday is this is how we can see different colors of light, okay. Let's look down at this image. You guys should have this as well. We talked about how this first image here is the electron at its ground state, and we're adding some sort of energy here, okay? This energy is allowing for the electron to jump up to that next energy level by increasing our amplitude of the waves. Does anybody recall the analogy that we used to help you remember the electrons jumping from energy levels? Those who were here Friday. Nobody? It related to Halloween, possibly? Oh, Ashley, yes.
It's like the sugar high.
Yes, the sugar high, yes. Similar to when you have a sugar high, you eat a lot of candy or a lot of sweets, okay? You get an increased amount of energy, right? But after a certain amount of time, maybe like an hour or so, that energy goes away, and you crash back down to your, well, normal state. Tired probably, but similar. That's what the electron is doing. That energy is being added, it's jumping up to another energy level, and then it drops back down to its ground state. And when that happens, energy is being released, and we're going to see different colors of light depending on which energy level it jumped to. Okay? That was mostly old information. We're going to move on to new information now. Okay? So this is where you might want to start using your colored pencils to highlight these lines here once I start talking about them. Okay? And you're also going to need them for the Bohr models on the next couple of pages. So, as I just stated on the previous slide, the amount of energy absorbed or released can determine the color of light that we see. Now, what we're going to be focusing on in this class are the colors red, green, blue, and violet, or purple, whichever. Okay? You will be responsible to know and understand which color is emitted depending on the energy levels that it jumps to. Okay? Key thing to note, you may want to write this down or circle it because you have this image on your sheet. We are going to be focusing on electrons jumping from the energy level 2, okay, from 2 up to some other energy level. This is because if we are focusing on electrons jumping from an energy level other than starting at 2, that is not light that we can see visibly, okay? So that's why we are focusing on starting at energy level 2. If you need to circle that to remember, please do. All right, so actually looking at this chart and what it means. So you can see this yellow line here is kind of showing us what it looks like when energy is being absorbed. So we're adding something similar to like the flame test on Thursday. We're adding the flame or electricity to the electron, okay? And it has an ability to jump energy levels depending on how much energy is added. So as we can see here, our baseline is that energy level 2, as I just stated before, okay? If we want to look at our red line first, okay, we can see that from energy level 2, okay, the energy added to the electron allows it to jump up to energy level 3, okay. When it drops back down to its ground state, that is where we see a red light emitted. So from 2 to 3, it also is labeled over here, okay, that's where we see red light. Now you can see that we give you some wavelength values there. We're not making you responsible for knowing the wavelength values, like I said. You're going to be responsible for knowing the color that's emitted based on the jumping from energy level to energy level. Okay. Now if we look over at green, okay, we see that, again, energy level 2. Oops. Sorry. Okay. We're jumping from energy level 2 to energy level 4. Okay. When we drop back down to our ground state, energy is released and we see green light. I'm hoping you're starting to see a pattern here of what I'm saying. Okay. Looking over at blue light, energy level 2 up to energy level 5. We drop back down to ground state, energy is released, we see blue light. And finally for violet light, this is our most energy, okay, being added, okay. Our biggest jump is from energy level 2 to energy level 6. Drops back down to ground state, energy is released, and we see purple light. Thumbs up, thumbs down, thumbs sideways, please. Need to see where we're at before I move forward. Fantastic. All right, now we're going to talk about how we can use the Bohr model to visualize this. Okay, make sure I have the right color here. So if you recall, we can use the Bohr model to label where our electrons are, okay, how many energy levels that element might have, okay, where they're sitting, the 288 rule, all that jazz we talked about earlier last week. We can also use the Bohr model to visualize our electrons jumping from energy level to energy level and show the color of light that is being emitted. On your sheet, sorry, okay, you guys don't have all of these energy levels. This one has all 7. I believe yours only has 4. You may need to add a couple to that first Bohr model. In the future, we are going to be using ones with all 7, so you won't have to worry about that. Apologize, that's my fault. So let's talk about our color that releases the highest energy and has the highest frequency, which is our violet light here, okay? And these waves have the shortest wavelength. If you remember, our wavelength and frequency has an inverse relationship. So if we have a high frequency, we have a short wavelength. We remember this, I hope, yes? And when we're talking about this type of relationship here, with our jump for violet, we're gonna see bigger jumps. And what I mean by this is we're going to be going from our energy level 2, okay, back and forth, energy level 6. Again, this is the portion you're going to need to remember, especially for your flame test lab report and for on tests, to be able to understand if you see violet light, you need to know it jumps from 2 to 6 and then how to draw it. And I'm going to show you how to do that. If I'm looking at my Bohr model here, I have my nucleus in the middle. I'm going to count out energy level 1, 2, 3, 4, 5, 6, 7. You can do that if you'd like. I do it just to remember. As I stated, we're always going to be starting at energy level 2. So when I'm labeling, I'm going to draw my electrons starting at energy level 2. And to indicate the jump with energy added, I am going to draw an arrow up to energy level 6 here. And I am going to write, this is where energy is absorbed. This is what you need to be writing on your Bohr model as well, please. So this is indicating my energy being absorbed, the excited state for the electron, okay? I'm writing energy absorbed so that I know that you guys know the difference. Now on the other side, okay, when our electron is dropping back down to ground state, I want to draw an arrow indicating it's dropping back down to energy level 2, and I'm going to write this is where my energy is released, emitted, whichever word you'd like to use. This is where you're showing me that you understand where the jump is and you know which direction, okay, that you're seeing energy absorbed and energy released. Last part that you're going to need to do, I want to draw a violet light, knowing that violet light has a high frequency and a short wavelength. When I draw the energy that's being emitted, I want to make sure to replicate what that wave looks like. So based on what I just drew here, short wavelength, high frequency. You guys also need to be able to draw it that way. You can't just draw a squiggle and say, okay, here you go. We need to be able to know that you understand, okay, it's violet light, high energy, high frequency, short wavelength. One more time, thumbs up, thumbs down, thumbs sideways. I just want to make sure that we are on the same page so that I can move forward and maybe just go a little bit faster. But I don't want to go too fast if we're kind of not feeling it. All right. So now we talked about violet. We're going to talk about our lowest energy and our smallest jump, which is red light. So you can see, based on the description here, frequency and energy are lowest in red light, which means that we have a smaller jump. Okay. These waves have the longest wavelength. And what this means for red is that we're going to see a jump between energy level 2 and energy level 3. This is a different Bohr model now. This is the one that you guys should have on your papers. This is how I'm going to label mine. If you want to label yours differently, as long as you understand which energy level is which, that's okay. We're not going to worry about the protons and neutrons because I am not giving you a specific element right now. It's just the Bohr model that we had been using before. All right, bless you. All right. Energy level 2 is where our electron starts for all of these. This is a short jump compared to violet, so I'm going to show my arrow to energy level 3. Energy absorbed. I'm going to indicate on the other side with another arrow here. Energy released. And then similar to violet, I am going to draw my red light being emitted. Now this wave should look different than violet light. We have a low frequency and a long wavelength. So your line should look something like that. You need to be able to understand that you understand what these waves would look like.
In addition to the color difference, we should see a difference in your wavelength.
Yes, absolutely.
It should not look like they have the same wavelength.
Mm-hmm. Am I all right to move forward? One more Bohr model to do. Yes, no, maybe? Okay, forward then. Okay, last one we're going to talk about is green light. You can see that it says orange under here with a question mark. We're not going to give you orange. We're going to give you some hints to think about orange. You should have saw in your flame test lab on Thursday, the colors emitted should have been red, green, blue, hopefully purple at some point, hopefully. And you definitely saw orange in there as well. So you will need to be able to indicate some information about orange. And we'll give you some hints for that, but we will not give you the Bohr model for orange. So, for green light, similar here, I'm going to label 1, 2, 3, and 4. If you remember back from our chart, green light has an energy level jump from 2 to 4. 2 to 4. Starting with my electron at energy level 2, indicating my jump to 4. Energy absorbed. Other side, I'm indicating my arrow back down to ground state. If I can spell, energy released. And then for green light, so our violet light had high frequency, short wavelength. Red light had the opposite, long wavelength, shorter frequencies. Green light is kind of in the middle. So when you draw this, kind of give us something in between purple and red when drawing out the wave. So I'm gonna add just like a couple more waves to it than I did for red light, but still less than violet light. When talking about orange light, so let's think about this a little bit. So try to think, when it comes to thinking about orange light and what's being emitted, where is orange on our visible light spectrum? What colors is it between? Okay. Also think about whether or not this is just one electron, one atom that this is happening with, or if it's multiple. Those are your hints for orange light. So you can write those down. I'll say it again. Think about where orange is on the visible light spectrum. What colors is it between? And also think about whether or not this is one electron, one atom, or if it's multiple that this is happening to, based on what you did with the flame test. Okay, I'm going to move forward now from Bohr models onto our last chunk for today. Okay. Energy calculations. If you recall from early last week, Tuesday and Wednesday, we started calculations with waves. So the first one that we talked about was our S is equal to wavelength times frequency. Okay, just for general waves, solving for wavelength, solving for frequency. We then upgraded from that to speed of light equal to wavelength times frequency, with our speed of light being 3 times 10 to the 8th meters per second. All right, maybe write this down today. You're going to need it, possibly. So this was just general waves. This was for light waves. Now we're going to calculate energy being released, or possibly solving for frequency. Those are the two options with this calculation. So that would be energy is equal to h times frequency. H is our new constant. So similar to how we gave you a constant for speed of light, we are going to give you this for h. This is Planck's constant, 6.626 times 10 to the negative 34th joule seconds. So this actually indicates J times seconds here. Okay. Planck's constant. Simpson, would you like to share your tidbit of real life today? Real life.
Real life. Okay, so for those of you who watched Stranger Things, Planck's constant was used in one of the episodes. I thought it was season 2. Told me first hour, it was season 3, whatever, it was one of them. So, and they're breaking into a safe, and I don't even remember what was in the safe that they needed, but they're breaking into the safe. Dustin is trying to get the safe open, and he's on the phone with his girlfriend, Susie, and Susie's like super smart, and she rattles off the value of Planck's constant to way more decimal places than we're gonna have you guys use, and that was the combination to open the safe. All right, so he entered in 6.626 something 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 something, and then there was something else they had to do with the negative 34 whatever. So if you didn't watch it, I didn't ruin anything for you because I don't even remember what was in the safe. And if you do remember, then you know what I'm talking about, but there you go.
So yeah, chemistry and
Chemistry
real
and
life.
Media.
Media. All right, so that's H. Again, we'll give that to you, okay? E stands for our energy, what we're solving for, and that unit is gonna be joules. Please use J, okay? Capital J, because again, that's named after someone famous who came up with the joules constant or unit, okay, equation. It's not spelled like jewelry, it's actually spelled like this. So please do not write out Jewels, not the same, okay? So just use J if you're unsure. And then V, or fancy V, sorry, is our frequency, and that's in hertz, which is 1/seconds. As you can see, with our Planck's constant, this is our joules times second. Our frequency is 1/seconds. That is how we get just joules for energy. Okay, those seconds are gonna cancel out. All right, I'm gonna move forward now and we're gonna do some practice. All right, some example problems. So this first one, given that the frequency of red light is 4.05 times 10 to the 14th hertz, what is the energy of the photon? Does anybody remember what a photon is? You do need to know what it is. Anyone? Talked about it Friday, I think. It was Friday when we did the spray paint and the flashlight demo.
It's a light particle.
Yes, light particle. I'll write that there just in case. Light particle. You need to know that, so I'll keep that there for you. So this question, the way that it's set up, is a plug and chug equation, right? We know that our equation is going to be E is equal to Planck's constant times frequency. So we are solving for E. Planck's constant is a constant, right? We give that to you, 6.626 times 10 to the negative 34 joule seconds. And then we're given our frequency, 4.05 times 10 to the 14th hertz. Right? So now it's just plug and chug, right? Remember, you do need to show us your units somehow in this, whether you set it up this way and put all your units here, or if you set up the actual equation and put your units there, you have to show us units somewhere, okay? I'm gonna do it in both because I can't stop myself because that's how I've always done it. So this is gonna be our Planck's constant times our 4.05 times 10 to the 14th hertz. Will somebody please plug this into your calculator and please give me the answer with units and proper sig figs. Remember, we look at the original value for sig figs.
2.68 times 10 to the negative 19.
Times 10 to the negative 19th. What is the unit? Joules. Fantastic. Are we all good with this style of question? You had everything you needed given to you to calculate the energy. Yes? Now let's move on to one that will be similar to something you might see on a test. Hint, hint. Maybe star this. Okay. So what is the energy of an ultraviolet photon having a wavelength of 1.18 times 10 to the negative 8th meters? I'm going to drop down our equation over here. E is equal to Planck's constant times frequency. What's the issue here? Based on the problem given to us. Does anybody notice anything weird? Lucas,
You don't know the frequency.
you don't know the frequency, right? But what did it give us?
Wavelength.
Wavelength. Do we recall a way to solve for frequency in the past? Maybe last week we had an equation for that. Maybe I told you to write it down to remember it. No? Okay, that's fine. I'm going to give it to you. So if we have wavelength, okay, that's not part of our energy equation, but frequency is. So we need to find a way to solve for frequency. Good thing we have an equation from last week that we can use to do that. And that is our speed of light equal to wavelength times frequency. Two-step problem here. We need to solve for our frequency, and then we'll be able to plug in everything to solve for energy. So, C is equal to what, if we remember?
3.0 times 10 to the 8th.
Yep, 3.0 times 10 to the 8th
ms.
meters per second. What was this, if you remember?
Speed of light.
Speed of light. Nice. We are given our wavelength in this problem. 1.18 times 10 to the negative 8 meters. And then, sorry, I'm running out of space here. Oops. We're solving for frequency. So if I plug everything in, speed of light equal to our wavelength times our frequency, which we do not know. This is a problem that we did last week. What did we get, Megan?
1.68 times 10 to the negative 17.
1 point. I'm not sure. Somebody double check that for me really quick. I thought possibly it started with a 2, but maybe I'm wrong.
0.54.
Okay, that's what I remembered. So double check your math on there. Maybe your exponent was off. 2.54. Can you give me up to 4 decimal points just for this?
2.5424.
24. I'm only saying that because, remember, we acknowledged that if you can keep the value given in your calculator to use for your calculation and just drop it down, it gives you a more accurate answer. So that's why I'm having you go out to 4 decimal points for plugging into the next equation. It was times 10 to the what? 16th. And what's the unit? Hertz. Yes. Frequency is hertz. Nice. Do I now have everything that I need to solve for energy? Awesome. So now we're going to use our energy equation. Okay. E is equal to Planck's constant, which is H, 34 joule seconds. Switching sides, sorry. Times our now calculated frequency, 424 times 10 to the 16th hertz. What do we get now with units and proper sig figs, referring back to our initial value here in the problem? What do we get? Oh,
At this time, seniors are heading back to class.
Fantastic.
Seniors are heading back to class. They should be all in class in a couple minutes.
Awesome. Fantastic. What was that, Lucas?
1.68 times 10 to the negative 17 joules.
Everybody else get this? Yes? Wonderful. Thumbs up, thumbs down, thumbs sideways on these two types of problems. You have 3 minutes left. You have one problem left. Start trying to solve that one. We will give you the correct answer tomorrow first thing.
Equality for nanometers.
Oh, yeah, that's probably good. Nanometer equality. What equal to 10 to the negative 9 meters? Yes? Let's try to solve this one on your own. Hint, hint, you might need 2 equations. Okay? And we'll give you the answer first thing tomorrow.